Good morning and welcome to today's Military and Aerospace Electronics webcast, Understanding the Future of Small Form Factor I/O, Deep Dive into the QMC VITA 93 Standard, sponsored by Elma Electronic with TEVS and Acromag. I am Jamie Whitney, Senior Editor of Military and Aerospace Electronics with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit to the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the Submit button. To refer a colleague to today's discussion, share it on social media, or access event resources, click the icons on the left side rail of your screen. A PDF copy of the slides are also available for download. Also, please be aware that today's session is being recorded and will be available on the MAE website within the next 24 hours. You'll be notified via email when the archive is available. Now I would like to introduce our panelists for today's discussions. Mark Littlefield, Director, Systems Products at Elma Electronic. Mark is Director of Systems Products for Elma Electronic. He is an active contributor to multiple VITA and SOSA technical working groups, including the SOSA Small Form Factor Subcommittee, and was co-chair of the VITA 65 OpenVPX working group. He has more than 25 years of experience in embedded computing, where he has held a range of technical and professional roles supporting defense, medical, and commercial applications. Mark holds bachelor's and master's degrees in control systems engineering from the University of West Florida. Jan Zimmerman, General Manager, TEVS Technologies. Jan is one of the two general managers at TEVS Technologies, a company located near Hamburg, Germany, and well known for their expertise in providing the highest quality I/O solutions. Together with Tim TEVS, he successfully managed the company's succession and is responsible for all aspects of the business, especially its strategy and business development. Jan holds a master's degree in business engineering from the Nord Academy in Hamburg, Germany. Robert Greenfield has been with Acromag for more than 35 years and is a co-chair of the VITA 93 work group. As Acromag's Director of Marketing, Robert is responsible for product strategy and business development. He holds a BSME from the University of Michigan and an MBA from Wayne State University. I'd like to thank our experts for their forthcoming insights, and thank you to our audience for their time and attention. So let's get started. Mark?
Hi, thank you everyone for joining us here. I'm going to start with just a brief introduction to VITA 93 or QMC, give you a little bit of background of what it is, why we worked on this standard, before passing it over to my colleagues for the more interesting technical aspects. So QMC is a small form factor mezzanine. It's a standard that we're in the last stages of drafting in VITA. In fact, it's really just going through editorial cleanup right now before being released to go to ANSI for final approval. It's like all I/O mezzanines, it's modular, flexible, and scalable in design. But specifically, it's rugged and reliable by its design. We designed it to support air and conduction-cooled environments and environments in which there's significant shock and vibration. It's really suitable for I/Os either from the front panel or for rear I/O in systems, and it's based on a high-performance connector. So the real inspiration for QMC came from another VITA standard, VITA 90 or VNX Plus. VNX Plus is a small form factor modular card form factor, and it has much of the same characteristics of its larger sibling, OpenVPX or VITA 65. It's got high performance connectors, it's rugged by design and such, but significantly smaller, about a third of the size of or volume per slot of 3U OpenVPX. Likewise, it had the same sort of mezzanine I/O need that a 3U VPX card has, which is satisfied by XMC. The problem is that XMC is too large to fit into VNX Plus. So we needed a solution for that. So we started this effort as a study group called VITA 85.109 in July of 2022. And we did produce a detailed report in early 2023. In that, we did a trade study of what mezzanines were available, what sort of performance they'd have, what sort of roadmap they would have with regards to technology growth over time. And what the conclusion we came to was that we really needed a new standard. The closest kind of analog to this is M.2, but M.2 is not really kind of designed for the modular I/O that we needed from a mezzanine, an I/O mezzanine expansion. So we kicked off the working group in March 2023 with several objectives. We wanted the mezzanine I/O small enough to fit inside a 19 millimeter VNX Plus module. It needed a host side connector using PCI Express and an I/O side connector with defined connectivity. It needed to have at least PCI Express Gen 5 performance. It needed to be deployable in either air-cooled or conduction-cooled environments, and it needed to support rugged environments, that is, kind of extremes of shock and vibration. We had some secondary goals, but they were still important. In addition to VNX Plus, we wanted to really support other form factors, things like VPX, VME, Compact PCI Express, and PCI Express Edge Fingers. And the reason for that is we wanted to be able to support kind of a wide range of deployable platforms and environments. So as you know, as we developed the standard and it kind of fleshed out, so to speak, we realized that there was going to be some real benefits to the market, and so it will have a real role to play in the market. QMC is really about one thing: its expansion. Mainly, it's I/O expansion. That was its primary goal, but we realized that it could serve other tasks like adding computation, things like small FPGAs or small GPUs, and even storage. There's no reason why it couldn't be used for storage. And as you'll see in my colleagues' presentations, how that'll be. So in effect, it plays much the same role as XMC does, but in a much smaller package. And like I said previously, is particularly well suited for those rugged environments. So we're already seeing effects of this, even though the standard is not published yet. Folks are doing preliminary design work, and we're expecting to see a broad ecosystem of I/O modules and carrier cards. Now, you actually should have mentioned one of the key goals that we had for this was that we needed to have good interoperability between the modules and carriers so that modules and carriers from different suppliers will just work. There was a great deal of work done in making sure that the mechanicals and the mountings were properly captured by the standard, and it's very clear what the carrier has to provide and what the module, the I/O module itself, the QMC module itself, has to supply. That's all captured in the standard. Like I said, rugged with high performance. It's going to be suitable for lab, factory, or field deployments. And we're going to see this being used in fact, already plans are in place and work is being done to use it in some really challenging environments, things like autonomous vehicles, edge computing, and AI types of applications, again, out at that edge. So with that, I'm going to pass it over to Jan.
Yeah, thanks a lot, Mark. And hello, everyone. I'm Jan Zimmerman, one of the two general managers here at TAFES. And today I'll give you a technical overview of QMC. And I'll say, let's dive in right away. On that slide, you see the QMC on the right with its base size, which is 26 millimeters times 78.25. And at a first glance, this might seem very small, especially compared to an XMC or PMC. But I think when taken into account the shrinking IC package sizes since the 1990s, which is when the PMC specification was released, it is rather a perfect match. The small size allows us building, for example, single function modules without wasting PCB area. And in addition, carriers can easily provide multiple QMC sites, which allows system integrators to comply with their customer requirements by just plugging in one or more QMCs. The component height of 4.7 millimeters you see here is very well known from PMC and XMC, and I think has proven sufficient for most circuit designs. And regarding the connector, that is currently capable of PCIe Gen 6 up to an X16 link. And another topic that gets more and more important is supervising the health status of boards via system management. And here the QMC offers an elegant approach to be seamlessly integrated into managed systems. So that means that the QMC can be managed and supervised by the system management, but it does not have to. And regarding the IOs, the IO count of the QMC, of a single QMC that you can see here on the slide, it comes with 40 IOs, which is a very high IO density on such small board. But it's not only the high IO density, it's also the IO speed. And that allows its use with high-speed interfaces, like, for example, Ethernet or Vision. Next up, I want to talk about scalability, and mainly about the question, why is scalability so beneficial? The scalability allows us to use the standard for a whole range of applications, starting from simple I/O functionalities on a single QMC up to highest complexity solutions with a need for a high bandwidth and high I/O count. For example, if you want to utilize a Sync Ultrascale Plus as a SOM or anything like that. So the QMC designers can adjust the size of the QMC according to the functionality they want to implement. A quad UART, for example, will for sure fit on a single QMC. A large system on chip from, AMD or Intel, on the other hand, will definitely need much more. And what does it need more? It does need more PCB area, more power, more host connectivity, and usually more I/O lines. And to address these demands, QMC do not only grow in size, but also in power, connectivity, bandwidth, and I/O count, as you can see on the side. And also, carriers can be populated with combinations of single, double, triple, and quad QMCs, only limited by the amount of QMC sites and the PCI Express connectivity provided by the carrier, of course. So the same carrier could, for example, be populated with 4 single QMCs in case the customer needs a broad range of different I/O interfaces, or with a quad QMC for customers who demand for a high power and highest performance connectivity. And also anything in between, like a single and a triple or 2 double QMCs, it would all fit there as well. Okay, then next up, I want to talk about the host interface. The host interface connector that you see here on the right side provides everything that the QMC needs. And that is, first of all, power. So for low power designs, we have the 3.3 volt power supply. And for high power QMC designs, you'll definitely go for the 12-volt power supply with the option to use the 3.3-volt power supply in parallel for highest power demands, or simply to reduce the number of onboard power supplies. Then second, you need connectivity. The QMC's one and only system interface is standard PCI Express. This may sound a little limiting at a first glance, but instead it guarantees interoperability, because this way every QMC will work on every QMC side. And a single QMC already has the capability for PCI Express X4, which, as shown on the last slide, increases up to X16 for a quad QMC. Then third, you may need to supervise the board's health status via IPMI. And the QMC is definitely ready for IPMI and managed systems in general, but I think there'll be more towards that later from Robert. And then last, we have the JTAG interface, which allows thoroughly testing and factory programming of the QMC without wasting valuable PCB area for example, an onboard test or debug headers or something like that. Then let's talk about the I/O capabilities. As you can see, the I/O connector of the QMC uses the same 80-pin connector type known from the QMC's host interface on the previous slide. It provides 20 differential pairs per single QMC that could also be used as 40 single-ended I/O signals. And in addition, there is one ground pin for each I/O, and this really is critical for the signal integrity of high-speed interfaces. Then, as you can see on the right side, the I/Os are organized in 5 I/O pipes. They're separated with a red line there. And these I/O pipes provide structure during design and usage of the QMC modules. And each I/O pipe, which you can see a single I/O pipe on the right side of the connector, each of these I/O pipes consist of 4 differential pairs and their individual ground. That means that each I/O pipe has its own ground reference plane. And this allows us to support also isolated interfaces like, for example, 10G Ethernet. So that is a large improvement for the system. And also the I/O count, of course, gets up and up. As you can see there, it's 80 per double QMC, 120 for triple, and 160 for a quad QMC. Next up, I briefly want to talk about the cooling and the cooling methods, where we have air and conduction cooled. And here you can see the air-cooled version with the QMC on top and the carrier on bottom. And basically, the mechanical fixation concept for QMCs is very simple and based on one simple rule, which is the carrier provides all mounting hardware. On the one hand, that means that the complete mounting kit, including screws and spacers, has to be provided by the carrier or the carrier manufacturer. And on the other hand, this frees the QMC designer from worrying about mechanical stuff and also saves the integrator from compatibility issues. The standoffs that you can see are usually pre-mounted on the carrier, and then using the screws and spacers that come together with the carrier, you can secure the QMC on the carrier board. Spacers are used for an air-cooled QMC mounting to cover the space for potential heatsink of the QMC, because the QMC spec allows mounting of conduction-cooled QMCs on air-cooled carriers. Next up, we have the conduction-cooled version, where you can see the conduction-cooled QMC mounted on a conduction-cooled carrier, where only the skyline heatsink is part of the QMC, which is usually already mounted at delivery. You can see that on the top and the carrier on the bottom. And then Also, the complete mounting kit, including the thermal interface material, which is shown here in red, it has to be provided by the carrier manufacturer. So the design of the carrier's cooling structure is 100% up to the carrier designer, of course, as long as the mechanical envelopes are not violated. And that way, the concept ensures interoperability between all vendors. One special thing here is the thermal interface material shown in red, as it extends over the whole area of the QMC, providing a direct high performance thermal interface to dissipate the QMC's heat. And this is really essential to be able to deal with the amount of power dissipation which is possible with QMCs, and also a great advantage over, I'd say, the thermal interface concept of traditional mezzanine standards, but also more towards the power budget later. Then up to my last slide, where I briefly want to talk about stacking heights, where, I mean, we all know that traditional mezzanine concepts usually come with a fixed stacking height, often forced by the fact that the mezzanine provides all the mounting hardware. And this works well for systems that match this fixed stacking height, but is a drawback for systems that would allow for more stacking height. And that's why QMC allows 4 different stacking height, as you can see on the right, either 9, 11, 14, or 16 millimeters. And this variable stacking height maximizes the component envelope on the carrier, for example, on a CPU board or an SBC, resulting in additional space on the carrier. With that said, the QMC itself is and will always be the same. That means it fits onto every carrier independent of the stacking height of the carrier or the carrier uses. And consistent with the policy that the carrier provides all mounting hardware, it is also the carrier that dictates the stacking height of the QMC. Yeah, and that's it with my part. I hope I could give you all some valuable technical information of this new form factor. And now I'm heading this over to Robert Greenfield, who will tell you more about the implementation of QMCs.
Hey, thank you very much, Jan. That was great covering the basics there. So hello, everyone. I'm Robert Greenfield, Acromag's Director of Marketing and Business Development. And now that you've heard about the reasons from Mark about the development, behind the development of the QMC standard, and the technical specifications of the modules and carriers from Jan, let's talk about some of the considerations for system implementation. So first thing is Jan had already kind of touched on it a little bit, is the power budget. So on a single QMC module, you have 4 3.3 volt pins and 3 12 volt power pins. And with each pin rated at 0.6 amps and numerous power sources, a single width QMC can generate almost 30 watts of thermal design power. So that is plenty of power to drive FPGAs, GPUs, and other powerful signal processors. And if you're using double, triple, or quad width QMCs, you can just multiply that power budget depending on the size. So, of course, if you're using the full power budget, proper cooling or power management is definitely required. As the Spider-Man movies taught us, with great power comes great responsibility. However, the QMCs offer a variety of useful features to help dissipate that heat. The QMC is designed to support a standard integrated heat sink that can be mated to the metalwork on the carrier for conduction cooling, as Jan was showing you before. You can see the module up in the upper right-hand corner there shows with the heatsink pre-installed, and they're always the same size. So the heatsink could also be used as a heat spreader on a carrier card with a fan, as shown in the image below, where we've got a fan on a PCIe edge carrier card here. So, and with the variable heat stacks, you've got a lot of flexibility to for creativity on how to get rid of the heat dissipation. So so that really facilitates the implementation, whether you're going to use something like heat pipes or something really creative, airflow through or whatever. So moving on to the next issue is, as Jan mentioned also, is that the QMCs were designed to be IPMI ready. Now, many advanced chassis-based backplane systems with plug-in cards make good use of an intelligent platform management interface, or the IPMI. The IPMI is commonly used in sophisticated systems on VPX, advanced TCA, and micro TCA systems. So, what was I? Oh, sorry. So the QMC carriers can actually provide a controller or IPMC to interface the QMC module information to the system manager. The IPMC reads the information from the QMC module's EEPROM over an I2C interface. Now, various sensors, in addition to A to D, D to A, or GPIO, may be used on a QMC for the system to supervise module health status, such as temperatures, voltages, that are stored in the EEPROM. Now, no IPMC development is required for the QMC module, and the data format is defined in the specification. So hopefully the slides are advancing properly. So getting into the use cases and the applications. So a broad variety of I/O capabilities are commonly implemented using mezzanine modules. Popular functions provided by mezzanine modules include analog to digital conversion, discrete event measurement and control, serial communication, and signal processing. But with the high-performance connectors and a rugged, compact design, the QMCs are really ideal for embedded systems requiring real-time computing, high-speed Ethernet, and advanced communication interfaces. The ability to combine sensor and actuator interfaces with FPGA and GPU processors, plus a mix of avionics and industrial protocol transceivers, all on a carrier card or a single board computer, offers really unlimited possibilities. Common applications include test, measurement and control, simulation, signal and protocol conversion, image or video processing, for graphics or vision, adaptive filtering, sensor fusion, and of course, is becoming more and more popular, artificial intelligence and machine learning. So these applications are often required in defense and aerospace, and increasingly for unmanned vehicles. They can be used in industries like high-tech manufacturing, things like semiconductor production or medical imaging, on high-speed rail or other transportation systems, and also for scientific research, for energy, space, or physics types applications. Okay, so now we'll take a look at some of the carrier card platforms. As we mentioned before, it was designed to be used in a wide variety of architectures. So as we mentioned, a lot of these different embedded computing architectures can host QMC modules, so you can get a really high density mix of I/O capabilities. Small form factors like VNX Plus were really the inspiration for the system, but they can also be used on rugged 3U and 6U Eurocard platforms, such as VPX and Compact PCI Serial. Another popular platform would be the PCIe expansion cards that are commonly used in rugged servers and industrial PCs. It's also popular to use proprietary embedded PCs, often with a COM Express or a NVIDIA Jetson system on a module type CPU, and you can combine those together in a variety of different sizes. So the carrier card designers have the flexibility to mount the QMCs in any orientation, horizontally, vertical, or a mix of those. The only caveat to that is optional support for multi-width QMCs, depending on the number of adjacent sites. So if you had 2 horizontal and two vertical, you couldn't support a triple. But if you laid them all out in the same direction, you could go as many as the size of the carrier card would allow. So in the table here, you can see how many QMCs could be mounted either horizontally or vertically starting from 2 QMCs on a tiny VNX Plus carrier, all the way up to 10 modules on a 6U card, and a lot of different varieties in between. The other thing to note is that a triple width or 3 singles actually have a square dimension, so that if you had like a custom board that's, say, a 79 by 79 millimeters, you could mount 3 horizontal or 3 vertically. So let's take a look at some of the size comparisons from various mezzanine platforms through the history. Mark was mentioning that we considered the M.2 module. Also, the mini PCIe module is a very popular platform used in a lot of different systems. Acromag developed a more proprietary system, ruggedizing the mini PCIe with an AcroPack module. And then, of course, we've got the you can see the size difference with a PMC or PMC or XMC module, and also to the old IP module, which was very popular in the days of VME bus and compact PCIe. So one thing important to notice is that as system designers really require higher computing performance, they also want it smaller. So the current benchmark is really for advanced systems is really a XMC module on a 3U VPX, and you can see the size of a 3U VPX in the upper right-hand corner. But sometimes even that is still too big. Thus, entering the QMC on a VNX Plus carrier card, as you can see in the lower right-hand corner by comparison, which is roughly about the size of a credit card. So this is extremely useful in things like small payload tubes on UAVs. And the other important factor to note is that the QMC is really the only small form factor mezzanine that can rival the performance of an XMC while providing a defined integrated conduction cooling scheme with the heatsink. So you get a lot of that flexibility. So the next step to expand the utility of the QMCs is to find a scheme allowing carrier cards to plug in different field connectors to match the functionality of the QMCs that are being used. This is especially important for PCIe edge card applications, as well as for rear transition modules. It's really ideal for this, for the RTMs, because you can get a standardized breakout of the I/O to industry standard connectors. So these will be handled in new dot standards like VITA 93.1 and .2 to define micro expansion I/O modules, which would be called the XIOM, or a smart I/O micro module called the SIOM. So these are extremely small plug-in I/O modules for front panel I/O. Now, I like to say that this is kind of analogous to the variety of FMC modules that have different connectors that can plug into an FPGA carrier card using a standard mezzanine connector. In the case of an FMC, you would use the VITA 57, or was a C-Ray connector. In this case, we just use the same 80-pin QMC connector to connect these. Now, the XIOM interfaces to the QMC's I/O connector. In the case of a SIOM, or a smart I/O, it would interface to the QMC's host connector, the PCI Express. So what was it? If you take a look in the lower left-hand corner, you can see an example of a smart I/O micro module using an Ethernet controller like an I210 in an RJ45 port. Then we have in the middle, we have examples of single width XIOM modules that can provide RJ45 or SFP cages for Ethernet, D-sub or coax connectors, and also a variety of different USB ports. You could also have multi-width XIOM modules that could provide 68 or 80 pin VHDCI or SCSI connectors, access to flash storage, or a combination of these ports. Like you can see in the lower right, you could combine 4 SFP cages. So on that. So that is really what I have. So maybe now, so that summarizes the variety of the considerations for implementing a system on using QMC modules and carrier cards. And now we can go back to our host, Jamie, and the panel for questions and answers. And I see a bunch of questions have already been coming through.
All right, Robert, thank you so much. And he is correct. We have gotten quite a few questions already, so we're going to jump right in. As a reminder, if you would like to submit a question, type your question into the question window on the side of your screen and hit the submit button. Also, please stay to the end of the presentation to complete our exit survey, which will pop up on your screen. You can preview the questions now by clicking the exit survey icon on the left side rail. Okay, let's jump into your questions now. Okay. Robert, something you touched on a little bit was power, but what is the max power rating for a single QMC?
Sure. Yeah, let me go bring up that one, the slide. We can take over here. So as we have, there's 4 3.3 volt and 3 12 volt power pins. So in theory, you could go on a single width module up to almost 30 watts of thermal design power. So in our experience, a lot of the times, like we've put on an AcroPack, which is similar sized, we put a zinc ultra-scale FPGA, which has a multi-processor system on a chip. And I believe that was like less than 6 watts. So you really, with the up to almost 30 watts of power, you could really do a lot of things with, say, a GPU or an FPGA, especially in an air-cooled type situation. It might become a little bit more complicated if you're dealing with a conduction cooling. But you could also use things like thermal heat pipes in that. But plenty of power available to do with whatever you really want. And with the multi-width QMC modules with the different sizes, you could actually scale that up even higher. I believe up to almost 120 on a 4 quad width QMC module.
But to build on what Robert just said, there's plenty of power on the pins, probably more than you can actually extract the heat for. So we by design, we defined QMC so that there was a lot of flexibility with regards to the carrier, for moving the heat away from ejecting the heat from the system, if you will. So we wanted to provide the industry with a lot of chance for innovation with thermal management. And we think that's really what's going to drive some of the interesting applications for QMC.
Thank you. And Mark, another one I think you could answer. Instead of regular contact pins / lines, are there any provisions for coax lines, especially to 6 gigahertz?
So I am so happy that question got asked. I want to thank the viewer for asking that question, because that is going to be one of the follow-on activities. Once we get this in the can and it's published, Robert mentioned that we're going to be working on XIOM and SIOM, but in addition, I want to investigate how we could replace that I/O connector with something that would provide a coaxial high performance connector for that very application. At the last VITA Standards Organization meeting, I actually kind of put out a request to the connector manufacturers. Let's take a look at this and see if it's possible. I've been busy trying to get the standard out the door, so I haven't really followed up with that yet. But probably in the next few weeks, I'll be following up with the connector manufacturers on that very question. So I would say stay tuned. If you have any questions or thoughts about that, feel free to drop me a line. I'd be interested in talking with you.
Thank you. Does the QMC architecture support PCIe bifurcation? Jan, maybe you could take that one.
Yes, of course. So basically, maybe let's start with what is bifurcation. So, well, the bifurcation describes the capability of a PCIe switch to split their lanes into multiple smaller links or vice versa. So, for example, if you have an X16 link, that would transform into, for example, 4x4 links or 2x4 and 1x8. And to answer the question, if the QMC architecture is capable of that, the simple answer is yes, it is.
Thank you so much. Are the QMC modules going to be qualified to the same environmental classes as VPX and XMC modules as described in VITA 47? Who would like to take that?
So I'll take that one, if you don't mind. We expect, yes, that they will be qualified. I don't think every QMC module and every QMC carrier will be qualified to those levels, because it really depends on the market that the supplier is targeting with their design. But I know some of the work that's going on by some of the vendors, and yeah, we will see QMCs and QMC carriers qualified to those levels.
Perfect, thank you. What are we looking at for a realistic estimate for the release date of both the VNX Plus and QMC specifications?
Another great question, and I'll take that one. By the way, I chair, Robert and I both chair the committee that's drafting this. So I can say with authority that we are very, very close. We're right now just doing final polish on the document, finding little typos and misspellings and things like that. And I expect there to be just one more ballot within the committee before it's released to ANSI, and then from ANSI, if I remember correctly, the timeline, it takes about 8 weeks to get through the ANSI process and be released. So we can probably realistically see this published and in the wilds by, say, the May timeframe.
Excellent. And another timeline question. When can we start seeing the first products? Jan?
Yeah, I think that's a pretty good question. And I think you're all going to see the first products as soon as the spec's going to be released, since this is something that we all want to do, like develop the ecosystem for QMC, because this, after like Industry Pack, PMC, then XMC, and now QMC, this is really the next generation mezzanine cards. And that's why we're not going to wait long and just push out products right after the spec is released.
Yeah, I'll add on to that we currently have a variety of different modules in development right now. We're hoping for to release a batch of modules by the end of the second quarter, and some additional ones following after that. I figure TEBS probably has a similar type strategy, as you mentioned. So, and we're definitely inviting a lot of other vendors. I've talked to a number of people that are considering developing some other QMCs for things like avionics as well.
Yeah, we have a lot of products in development as well, so I can only relate to that. And yeah, as soon as the spec's out, there are going to be products for the QMC.
Mm-hmm.
Thank you. Are any of you gentlemen aware of any manufacturers currently making VNX Plus single board computers with QMC mezzanine sites?
Oh, I can say there's none actually in production at the moment. There is at least some preliminary design going on, but it's pretty challenging because the thermal design is a little bit hairy, and so people are being a little bit cautious about diving into that. So, but I can say that I've seen some preliminary design work done with that. So I have to expect we'll see something probably within the year.
Excellent. Okay, got a question about interoperability. Is there any plan to define templates that assign specific functions to the non-PCIe connector?
Right. I'll float that one too, if you don't mind, because that was a topic of great discussion within the working group. At the moment, we are not defining specific functionality on the I/O connector. The carrier standards are addressing the questions with regards to how to map QMC to backplanes, for instance. So like VITA 90 will capture how those signals mapped to the backplane, but much like with OpenVPX and XCIO. But at the moment, we're not going down that path. We're leaving it open. There might be good reason why we would want to define specific functionalities. But like XMC, the real power of the I/O mezzanine is that you can say, design a system today using a carrier card, like an SPC and a QMC module on it. And then say in 4 years, 5 years, you want to do a technology refresh. You can take that carrier card, replace it with a different carrier card, but keep the QMC the same, and you keep the same functionality and the same mappings. And so that's really where the power of QMC is going to come from.
Thank you. Is there a reason why 16 millimeter is the max stacking height? Might be a question for Robert. Do you have an answer for that one?
Yeah, really, because we're designing around the Samtec connectors, and the connector height on the QMC module is defined as always being 7.5 millimeters. But there's a variety of other sizes, but the maximum size when you made it to the carrier card connector is 16 millimeters.
Thank you.
Yeah, but I should add, though, that there may be, and again, we wanted to try to allow for as much flexibility as possible within the industry. There may be cases where you would want to use a QMC in, say, a very high power environment or high temperature environment, and you need that extra space for cooling structures. And so, we wanted to make sure that if it was needed, it was there.
Thank you. And how does the new QMC standard match with SOSA and MOSA? Jan, maybe you want to take that one?
I think that's a question for Mark rather than for me.
My apologies. Mark, would you like to answer that one?
Sure. So as I mentioned at the beginning, this came out of a need from VNX Plus. And VNX Plus is very, I would say, driven out of the desire for supporting the MOSA concept, and specifically the SOSA, the Sensor Open Systems Architecture standard. It's captured, VNX Plus is captured within that standard, and QMC is going to be supported by VNX Plus, so it's kind of by inheritance captured within the standard, and so it's very much in line with the spirit of MOSA that's captured within the SOSA standard.
Okay, and we've got another question about size. How did the work group settle on the size of 26 by 78 and a quarter millimeters?
I can take that one. Well, we went through a lot of different iterations. As Mark said, we spent a lot of time in the study group really taking a look at this. The starting point was to make sure that we could fit at least 2 modules on a VNX Plus carrier card. So, because we had the mini PCIe, which was 30 millimeters wide, so you couldn't put 2 of them on a 19 millimeter when you had like a 400 pin connector, I believe it is. It wouldn't fit. So that's how we started getting to that 26. And we had basically like a M.2 being 26 by 80 millimeters also kind of gave us an idea of a starting point. But then as we started looking at other platforms, especially like 3U VPX, and taking a look at the heat frames and the wedge locks and different conduction cooling and where the mounting came, trying to figure out how to maximize this to fit as many QMCs as possible on it. We started narrowing it down little by little, we thought we were done at about 79 millimeters, but then we figured out that for maximum 78.25, and that's where it stuck, that we thought would really offer a lot of flexibility. It didn't impact how many components you could put on the board, and then you could really use it on a variety of different form factors. And it also gave that nice little square size when you did a triple with the spacing in between adjacent modules. So you had, what was it with, I think it's a quarter millimeter between them. You get that 78 by 0.25 by 78.25.
Okay, thank you. Looking at implementing a QMC in a 3U conduction environment, it looks like line the connector would cut into the thermal path of any components under the QMC. Have any studies looked into the impact?
So to answer that question, I would say yes. We've studied that a lot. We studied it in both the study period of the working group, as well as the drafting of the standard. We understand. I would say that we looked at both air cooled, where the air needs to flow, and the effects of the blocking, if you will, of the connectors, as well as in the conduction cooled environment, where that heat is going to want to move and how you're going to have to create thermal structures on the carrier to move the heat away. So this is probably a good opportunity to point out that we're drafting a design guide that will be published after the standard is published, that talks a little bit about this and looks at some of the things that we looked at within the committee, things that weren't really appropriate for the standard itself, but is good information, say, for the market and for a designer who's taking the standard and say, geez, how can I use this? And so, yeah, we studied it, but there's, I think, also plenty of opportunity for designers to innovate and come up with interesting solutions to that problem.
Okay, thank you. And what do you folks see as applications as prime targets for this technology?
I think, as Robert mentioned, the possibilities are pretty much unlimited, or almost. And I think anywhere really where like swap C requirements are necessary, that, and also like where the QMC was designed to be very modular, flexible, and scalable. So basically not only building on today's I/O, but also taking into account requirements for the future, as it's the next generation mezzanine I/O, I would say. It's definitely something that could be in like small rugged boxes as well.
Okay,
Yeah.
Sorry, go ahead.
Yeah, I'll kind of add on to that. We're kind of taking a look at being in the mezzanine business for a long time with industry packs and mini PCIe and XMC. We're looking at a lot of the same type of defense, aerospace, and manufacturing type applications. We've gone through a lot of effort to keep the QMCs economical to be used in industrial manufacturing, but also be very rugged and capable of being deployed in these military and defense applications as well. So those are the same kind of things that we're looking to see.
Excellent. I'm going to say, obviously, a lot of application uses, opportunities, and positives. But what sort of challenges or gotchas do folks need to be aware of?
I would think probably the number one challenge is thermal, and I've mentioned that a few times. This is a really small board, and the single width, and people are going to want to push that to their limits. They're going to put things like FPGAs on there and other relatively high-powered components, and so your power densities can be very high. So I would think that the number one challenge is going to be, how do you manage the heat? And the fact that you've got QMCs from one supplier and carriers from another supplier means that that combination of carrier and QMC might not have actually been tested ahead of time. And so the system engineer is going to have to kind of really look at the type of environment that they're going to be deploying into, and really kind of do their homework and make sure that they're going to be able to cool the QMC properly in that deployed environment.
Excellent. And we are coming up to the top of the hour, so I think I will end with just one more question. How does QMC compare to XMC in performance?
I think I can answer that. Well, if we look at an XMC module and compare it to, for example, a quad QMC, you'll see that the quad QMC is about, I'd say, 25% smaller than the XMC. And an XMC, according to VITA 42, is PCIe Gen 4x8, if I'm correct. And the QMC, or even a dual QMC, is or supports PCIe Gen 6 up to an X8, and a quad QMC supports Gen 6 X16. So we're like the QMC is much higher. And also regarding I/O, I think the XMC P16 has 144 I/O pins, and 4 QMCs. A quad QMC offers 160 I/Os, and yeah, other than that, both support IPMI, both standards support conduction cooling with a heatsink, and then we have the stacking height that is variable with the QMC and fixed with the XMC.
Excellent, thank you. And with that, I'm afraid that we have run out of time. For those questions we didn't have time to answer, we'll be getting back to you via email. And that concludes today's presentation. On behalf of Military and Aerospace Electronics, I'd like to thank Robert, Mark, and Jan for their presentations today. OMA Electronic for sponsoring today's webinar, along with Taves and Acromag. And of course, all of you for joining. Have a great rest of your day.